Welcome to homework.
All right, this problem is involving test score results from the TIMSS test. And it tells us that the United States scored an average of 508. It also tells us that the United States had a standard deviation of 72. It tells us that we're going to take a random sample of n from the United States. And then it gives us a whole bunch of information about South Korea, Singapore. That is just added information just for your own knowledge. So the question here is saying if the probability that the mean of that sample exceeds 520 is 0.0985, what is the sample size? So ultimately, we're trying to find this n value. So something else we know then is that the probability that the average of whatever sample that was exceeded 520, and we know that probability to be 0.0985. So we're going to start by drawing a bell curve. And we are going to put the 508 in the middle. And we know that we're talking about the magic number 520. And we know that greater than that is the 0.0985. Now we also know that the entire bell is a 1. The area under the curve of a normal distribution is 1. So that means on the left side is going to be 0.9015. So what we want to do is we want to figure out what the z-score is that's associated with 520, because then we can use our z-score formulas to help us figure out what n is. Now in order to find the z-score here, we're going to have to use the inverse norm feature on our calculator, or we can look up this 0.9015 in the interior of the standard normal table and work our way back out to the z value. Now sometimes using the table is a little more difficult. You might not find that 0.9015 exactly, so you end up going to what is close. But we find that the inverse norm on the graphing calculators provided by Texas Instruments is relatively easy as well. So I'm going to take you through that. I'm going to bring in my graphing calculator. And with my graphing calculator, you are going to access the inverse norm feature by hitting the second button and then hitting the variables button. And you're going to see a drop-down menu, and we're going to select number 3. And on your home screen, you should see inverse norm. Depending on your operating system, it might ask you a couple questions. So notice underneath it asks you for the area, and it's talking about that area to the left because our table in the book also refers to the area to the left. So we're going to put in 0.9015. It then asks us for the average. Well, if we're talking in terms of z-scores, the average on the z-score, or the number that corresponds with the 508, would be a 0. So we're going to type in a 0. Whoops, follow it up, back up. We need a comma, followed by the 0. And then it asks you for the standard deviation. Well, on the standard normal curve, the standard deviation is a 1. So we would type in a 1. And we'd close off the parentheses, hit enter, and we find out that the z-score associated with 520 would be a 1.29. Now again, if you used the table in the back of the book, you're going to be looking for the number on the inside that's closest to that value. And then when you scoot out this way, you'll see the 1.2. And then when you went up, you were going to see the 0.09. And that's also how I would get 1.29. Now that I have the z-score associated with that 520 magic number, I'm now going to rely on my formulas. And my formula for averages and z-scores would be z equals x bar minus mu sub x bar over sigma sub x bar. And we can rewrite that formula to say x bar minus mu, because the average of the sample means is the same as the average of the population, all over sigma divided by the square root of n, because the standard deviation of the sample means is also equivalent to the standard deviation of the population over the square root of the sample size. So using that second formula, so I'm going to rewrite that second formula, we have z equals x bar minus mu over sigma over the square root of n. We can fill in majority of that formula. We know the z value now is 1.29. We know that the x bar is 520. We know that the average of the population is 508. We know the standard deviation of the population is 72, and we don't know n. So now it becomes an algebra problem. So I could say 1.29 is equal to 12 divided by 72 over the square root of n. I could cross multiply, and I could say 12 is equal to 1.29 times 72 over the square root of n. That's just using cross products to solve a proportion. I could then say 12 equals 92.88 over the square root of n. I can do cross products again and say 12 multiplied by the square root of n is equal to 92.88. I can divide both sides by 12 and say square root of n is equal to 7.74. And then I could square both sides to undo that square root, and I will get n equal to 59.9076, or n is approximately 60. So the sample size that I would have used to assure that the average of the sample was greater than 520 to be 0.0985 would be approximately 60 individuals.